Good afternoon, everyone, and welcome to today's webcast titled Brick by Brick, How to Develop a Water Quality Model. This webcast is sponsored by EPA's Water Quality Modeling Workgroup, and I am Jason Gilday. I'm with US EPA, and I'll be moderating the webcast today. Thank you all for joining us. A few housekeeping items before we begin. We hope that you have a lot of questions. You'll note that we've changed from Adobe Connect to GoToWebinar, so the format might look a little bit different to you. There is a questions box on your control panel. You can type in questions there and click Send. If your control panel is not showing at this time, simply click on the small orange box with the white arrow to expand it. If you have any problems viewing the broadcast, just let us know in the questions box, and we will post an answer in that same box. A phone number is also available on your control panel if you are having trouble hearing audio through your computer speakers. This webcast will be archived for later viewing on EPA's Water Quality Modeling Workgroup page, and we will provide a link for you on a slide at the end of this webcast. Also, at the end of today's webcast, you will be able to obtain a certificate of attendance for participating, and we'll provide directions for downloading it at the end of the webcast. The materials in this webcast have been reviewed by US EPA staff for technical accuracy. However, the views of the speakers are their own and do not necessarily reflect those of US EPA. Mention of commercial enterprises, products, or publications does not mean that US EPA endorses them. So with those housekeeping items out of the way, I'm going to kind of get things kicked off now. As I discussed at the first webinar a month ago, this series is brought to you by EPA's Water Quality Modeling Workgroup. Essentially, we're a group of EPA staff members at EPA headquarters and the regions who use models to solve water quality problems, and most of us at this time are in the TMDL and standards programs. Our group was formed kind of mostly as a grassroots effort to facilitate collaboration among the people that use models, and we're led by the steering committee that you see on this slide. We are excited that we're able to put on this webinar series, which will mostly be presented by EPA staff. And as you can see, the last time the speakers were myself, Jason Gilday, and Tame Sheikh from Region 6, and today it's Dino Marshallonis and Ben Cope from Region 10. The purpose of the webinar series is to help water quality professionals better understand water quality modeling and how models can be used to solve the problems facing water quality regulators. The target audience for the series is essentially a water quality professional who may want to use, want to use, or review models as part of their job. But you don't necessarily have a modeling background, and I think that encompasses a lot of us out there. There's a lot of us out in the world doing water quality work, but we're not all PhD experts in modeling, and this series is designed to kind of bring everyone up to speed. As such, we're assuming that the audience has a basic understanding of water quality science and concepts, but has limited direct modeling experience. To reiterate from last time, there's a wide range of topics to discuss with water quality modeling, and this webinar series is really designed as a broad overview or intro to water quality modeling. The webinars will build off of each other, so I encourage people to attend all 6 if you can. And also each webinar will be recorded, archived, and posted to EPA's YouTube website. The first webinar is currently posted, and a link is also available on our Modeling Workgroup website, which we'll be posting at the end of today's webinar. So today's webinar is the second in the series, and it builds upon information presented in the first. The webinar series has been constructed to begin with water quality modeling basics, webinars 1 through 3, as you see on the slides on your screen. And then we're going to move into some more specialized modeling topics for webinars 4 through 6. We're still deciding on how to best put together webinars 4 through 6, but I think webinar 4, we've pretty much settled on doing some nutrient modeling and presenting some experiences that we've had with that. But we intend to use the feedback that we get from the audience from the first 3 webinars to kind of guide how we do the last 3. Our speakers today have prepared materials that will explain key steps in the model building process, including quality assurance project plans, or QAPPs, model selection, model setup, calibration, error uncertainty evaluation, and model acceptance for decision making. Our speakers today are Dino Marshallonis and Ben Cope, and without further delay, let me introduce them to you. Dr. Dino Marshallonis is a biologist in Region 10's Office of Water and Watersheds. Since 2010, Dino has worked as a hydrology modeler assisting the NPDES permits and TMDL program, as well as the Office of Compliance and Enforcement. Most of his work focuses on using watershed models to predict stormwater runoff and to evaluate the effectiveness of various DMPs in reducing water quality impacts to receiving waters. Ben Cope is also presenting today. He is an environmental engineer in Region 10's Office of Environmental Assessment. He began his career at EPA in 1988 in NPDES permits and later worked in the TMDL program. Since 2000, Ben has worked as a water quality modeler in the region's Environmental Assessment Office. Most of his work focuses on receiving water models for temperature, nutrients, algae, and dissolved oxygen. And I just want to give a big thanks to Dino and Ben for joining us today. So as a final note, before we kick off the presentations, we will try and answer as many questions throughout this webcast, and we'll be asking questions of each speaker after their presentation. Due to the high number of participants today, and I think we have over 400, maybe close to 500 people logged in, we may not be able to answer all of your questions, but we will be posting the speaker's contact information on one of the final slides. So with that, I'd like to hand over the presentation to Dino, and Dino, the floor is yours.
All right, thanks, Jason. Before we get started on today's content, maybe we should have a quick recap of what you and Payne discussed on the first webinar. You stepped through the audience, what is an environmental model. You talked about, why you might want to use one. You talked about different types of models that are available currently, and also examples of environmental problems that you could try to solve using the assistance of a modeling tool, and then a little bit about how to actually select an environmental model. Today's content will focus on the steps necessary to actually construct that model. I'm going to talk about the initial planning phase in the development of a quality assurance project plan, or QAPP, and then I'm going to hand it over to Ben, who will discuss the actual model construction process, model testing and evaluation, a process known as calibration, and then a little bit about determining model acceptance. Next month's webinar will focus on what you can do with your modeling tool once it's built and deemed acceptable. And I think all modelers out here really find that to be the most fun part of the process. But you got to start somewhere. And before we dive into that, I do want to remind everybody that a model is a tool to help us better understand a system. And it makes sense of complex processes and aspects of a particular environment from known aspects of the environment. It fills in our understanding of the system, it fills in those gaps. We need to know what information is out there about that system and what is not out there in order to decide how to best move forward in the development process. This is Region 10's Modeler's Creed, and I think it's applicable basically to all modelers. And so with that, let's begin our hypothetical journey down the road towards a successful modeling project. Every project has to start with a day one, and that's likely to be the scariest day of your project's life. You're going to be freaking out. You're going to be full of questions. You're not going to know what you're doing. You're not going to know how you're going to do it. You don't know how much money you're going to have to do it. You're going to have all of these questions, and you're not going to have any of the answers, but others will be there to help you, and that is why you need a project team. So here's a list of staff that you might want to include on your modeling project team. Obviously, you're going to need to have a project manager, someone that's going to keep everybody else in line in terms of budgeting and scope. But you're going to need the modelers themselves. And your organization might have a modeler already that can handle the task, but you might find that you might need to contract out to another entity to actually support the modeling effort. And then field staff that might be familiar with your water body or sampling locations is going to be a critical piece of the puzzle. I think of a situation where we're looking at a river and we're particularly interested in dissolved oxygen, for example, and your monitoring shows that there's consistent flows in the river, and then suddenly those flows drop off significantly, and right around that area you see very low values for DO. And you might say to yourself, well, what's going on right there? And you consult your field staff, and they say, oh, yeah, there's a wetland nearby. And you can say, okay, well, this is valuable information that I wouldn't have known if I just was looking at GIS information, for example. That's something that should be included explicitly in your model, and you should definitely consider later when you're assessing that model's performance. And that part, calibration, Ben is going to speak to in greater detail later. Another thing to consider is, what is the purpose of this model? Is it to inform a total maximum daily load or TMDL analysis, or is it going to be used in some sort of permit? And if so, you would want to have some staff with expertise in either TMDLs or permits. And then finally, depending on the project itself, you might want to include an attorney or upper management. And I think that's your organization's call, but I find that it's sometimes very useful to have those folks present as well. So the first thing you should do once you've formed your group is to get together and discuss with the team the needs of the project, any constraints or limitations, and what the expected outcomes are to be. You would want to gather everyone that is needed for the development of the model, but remember that this discussion is likely going to eventually dive into very detailed technical information, and some people might get bored or overwhelmed like that guy in the far left, but it's okay to over-invite. You would rather have more people there than to not invite someone that might have a valuable piece of information that would inform the overall process. This discussion should be as open and transparent as possible, and you should ask some really tough questions of each other. For example, can the model even give you the information that you want? Can it be done but at a reduced level of detail to achieve the same objective? Does the modeler that you have lined up even have experience with that model and the comfort level to actually make this project happen? Or do you need to hire somebody outside? And I think you should be as honest with yourself and the team as you can. Another big question, and this is one that we find in Region 10 to be particularly daunting, is do you have the data required to generate the model output that you want? And I think Ben is also going to speak about this a little bit later. So, just to recap, the more the team can get on the same page during this initial discussion, the less headaches you're going to have down the road. This is the time and the place where everyone's expectations should begin to align and synchronize, and that is a very good thing. So these are the 4 general phases of model development to consider during this kickoff project team meeting. The first phase is your team will create a plan for accomplishing that model development, and that's going to be documented in the Quality Assurance Project Plan, or QAPP. I'm going to spend the next few minutes discussing QAPPs in greater detail before I hand it off to Ben to discuss phase 2, which is where the model is actually constructed. Phase 3 is model calibration, and that is when the team together evaluates the model's ability to reflect observed reality. The final phase is when you have collectively come to agreement that the tool has been created correctly for the project's purpose, and then you can begin to play around with that tool to explore different scenarios. For example, maybe you're interested in how that system will work under different climate changes. Or maybe you want to apply specific BMPs, like adding in riparian buffer and looking at what the stream temperature changes because of that change. Note that Phase 1 and Phase 4 involve both science and policy, but Phases 2 and 3 really are strictly science. And so this brainstorming project team meeting might include some of the following agenda items or pieces of information for discussion. What are the processes that you need to explore? What is it that you're trying to study? This schematic here highlights various interactions of organisms, water, sediment, and air to drive ambient dissolved oxygen concentrations. If DO is what you're interested in, you will need to understand the characteristics that determine how all of these entities interact with each other. And you can see from the slide there are a lot of arrows or interactions of these different entities together. So it's a relatively complex schematic, and you're going to have information about all of that. What are the potential sources of pollution that might be modeled? Let's say you're looking at mercury getting into this stream shown in this schematic. Is atmospheric deposition of mercury a significant contributor to this particular area? Are there point source discharges from industrial facilities nearby? Or is stormwater likely a culprit in the loading of mercury to this particular water body? And so all of the answers to those earlier questions should help determine the type of model or models that you would want to focus on. The first webinar talked about the difference between a watershed model and a water body model, so I won't go into those in too much detail, but you should be aware that there are other types of models available. We have plume models that look at dispersion and mixing of discharges with ambient water. Let's say you're looking at a food web model where you want to know about the accumulation of toxic materials within a tissue of individual organisms. Or maybe you're interested in some model that focuses in on climate and how climate will change in the future. And of course, there are statistical models that are also available. Another consideration is, what is the level of detail that is required to be modeled? There are very complex environments like estuaries that have many rivers that feed into them. And in that particular instance, maybe a 3D model is most appropriate. Or maybe you have a lake that doesn't have a lot of data associated with it, and you think that you can explain what's happening with a simple mass balance relationship that ties in the differences between materials entering the water and those exiting. In that case, a 0D model could work. And there are a lot of models out there, and they all differ in terms of their options. I think the best thing to do is to combine your needed objectives with the shape and dimensions of the system that you're studying, and that alone will help you whittle down your model choices. The level of detail you need in your model will also determine the type of model you're going to choose. If a single value will be adequate for your purpose, let's say you just need a yearly average of sediment load to a river, well, that's going to be very different than if you need a fully dynamic model, which continuously updates model calculations every single time step based on varying input, like hourly precipitation. It is worth noting that as our computers get faster and we gain this increased computational capacity, that there is a greater, there's a trend for greater use of dynamic models. And I think personally, a lot of people tend to think of dynamic models as being a lot cooler, and so they tend to gravitate towards them. That may or may not be a good choice, and we'll talk about that a little bit later. So all of these ideas and thoughts and details need to be considered separately and worked out. And the location where all of this reasoning should be documented is in the Quality Assurance Project Plan, or QAPP. A QAPP documents the planning, implementation, and assessment procedures for a project. It integrates all of the technical and quality aspects of the project in order to provide a blueprint for obtaining the type and quality of data and information needed for that particular project. All work performed or funded by EPA that involves the acquisition of environmental data, including model-generated data, must have an approved QAPP. And I would like to highlight that EPA has guidance for how to develop QAPPs, including QAPPs specific for modeling. Document G-5M, creatively named Guidance for Quality Assurance Project Plans for Modeling, identifies the procedures and elements required for any EPA-funded project and includes example QAPPs for simple, intermediate, and even complex modeling projects. And you can find this document and others at the EPA website listed here. A good QAPP is valuable to a modeling project in the following ways. First, it documents all the criteria and assumptions in a single place for easy review and referral by anyone that's interested in the model and the project. And second, it can be used to guide the project staff themselves through the development process. I like to think of it as a roadmap for moving through in the development process. And it helps ensure that the choices made are consistent with the established objectives and project-specific requirements that were defined at the beginning. To be honest, model development is very confusing. That's one of the reasons why we are having this particular webinar right now. It includes a lot of detailed steps, and it's understandable that even experienced people could make mistakes. We all do this. A well-thought-out QAPP makes it easy for others to review the information on your model, and it ensures that nobody accidentally overlooked a critical step in the planning phase. So planning for modeling projects is just as important as planning for any other project. You know, I think of monitoring collection as a project that typically is associated with QAPPs, but modeling projects are just as important. In order to be able to use your output from this model for anything from regulatory purposes to research, you really should be sure that the model is scientifically sound, robust, and defensible. And a surefire way to ensure that this is the case is by following a thorough planning process that incorporates the following elements as shown here. And I will say that either I or Ben should hit on each of these bullet points throughout this particular webinar. So if you haven't gotten the gist that I really love QAPPs by the point now, I'm going to tell you a couple great things about QAPPs. One thing is that they document the process by which the team collectively evaluates and selects an appropriate model for that project. It explains the reasoning of why one model was selected as opposed to another. And I know Tame talked in the first webinar about model selection, so I won't go through these individual line items here, but just know that the QAPP helps document the decision that was eventually made. QAPPs also force the project team to consider the merits and ramifications of using a more complicated model instead of a simpler one. This can be a difficult decision, doesn't always have to be, but it should be informed by all members of the team. And you should keep in mind that there may be a single factor that strongly influences the ultimate choice, either a small budget or limited experience or resources, or perhaps there's even the threat of a litigation. In general, complex models have potential to provide greater detail, but that comes at a cost. They may require more assumptions which need to be justified and will likely require more data to drive them. They always seem to require more money. Unfortunately, that does not always translate into better or more reasonable results. Whenever possible, consider using the simplest modeling tool that will achieve the project's objectives. It will be easier to understand and easier for the team to defend later on. So here's one example of a very simple exploratory mass balance model applied to a river for a single pollutant, in this case phosphorus. As you can see from the equation, the data required for this spreadsheet model consists of flow and water quality measurements, both of the discharge effluent, but also the river itself. The plot at the bottom of the slide shows that the modeled estimates for phosphorus concentrations are quite similar to those actually measured. So the blue line is the model estimate, and the red dots are what was measured in the field. Contrast that example with this one from the other end of the spectrum. This image shows the model domain created for the Neuse River Estuary total maximum daily load, which is located in North Carolina. This project required a watershed model's simulated data output to link directly to a 3D water quality model as input. So the generated data from the first model actually drives the second model. Model calculations were made within each of those blue boxes during every single time step for a whole suite of different parameters. So, not to kill the point, but there really is a wide range in different modeling tools in terms of their capacity, and a huge difference in the resources and effort required to create them. Another benefit of QAPPs is that they force the team to identify data limitations, either from data gaps or poor data quality. Depending on the data requirements of your particular model of choice, the window of opportunity for the model simulation may be surprisingly limited. In this example, the model can only be run to simulate the time where you have data available, which is, in this example, July of 2009. Sometimes it's possible to make assumptions and create artificial data sets to fill in some of those gaps. But of course, those procedures and their rationale would need to be included in the QAPP. I like to think of QAPPs as a tool themselves for managing expectations for the team, sort of like a contract. It helps to give shape to the roles and the efforts for all of the team members, and everyone gets on the same page in terms of what they need to do, and also, maybe more importantly, what they don't need to do. And finally, QAPPs provide a preview opportunity for project peer review. Reviewers should include everyone on the project team itself, but if the project is particularly big or challenging, it may be a good idea to include external reviewers. And Ben will also discuss general model peer review towards the end of his presentation. But you'd be surprised at how many possible mistakes you can uncover early on in the process. For example, I was a part of a project team once where a model was created with data that generated monthly and daily averages, but we didn't find out until after that model was built that they actually wanted to examine individual storm events. So if we would have known that at the beginning, we would have built the model a little bit differently. So with that, I'd like to leave you with one other thought, and this is by Abraham Lincoln, who said, "If I had 6 hours to cut down a tree, I would spend 4 hours sharpening the axe." The point being that putting the work in ahead of time will make the task much easier. And with that, I think I'm ready to field some questions if there are any.
Thanks, Dino. We've not gotten a ton of questions, so I'll encourage people now to type some stuff in for Dino if you have anything. But we have a few, and the first one I'll just kind of lump together. There were a couple of questions just about QAPPs and how much effort goes into a QAPP and who develops it. So could you maybe talk about timeframes or funding or those kind of things?
Sure, I'll give it a shot. I think typically you have a budget for a project, and that could either be large or small depending on what the actual project is, and the QAPP would need to be developed within that budget. So it would be one particular task of the overall scope for that budget. You can have an in-house team develop the QAPP, or you can hire a contractor to do that. EPA tends to contract out, but we have also done our own QAPPs. It really just depends on the project team's expertise and if they want to take that on or not. In terms of the level of effort, I hope my presentation sort of pressed the point that it needs to be as thorough and detailed as it needs to be. You might have a very simple model, and so the QAPP would be maybe a little bit thinner. But if you're going to be doing some pretty heavy lifting in terms of modeling, you're going to have a lot more details that will need to be addressed, and they all have to be spelled out. And I think that's really for the betterment of the project.
Thanks, Dino. I've got another one here. So, modeling projects can be quite long, and there can be changes throughout the project. So I think the question is, what happens when your path forward deviates, or what you're doing deviates from the QAPP?
Yeah. So deviations are expected, and sometimes they're really good. Maybe you're on the wrong track, and I think. One of the benefits of the QAPP is that it helps you to keep an eye on that. It's okay to change course if you find out that you need to do that. The QAPP isn't necessarily set in stone, but it's just a good opportunity to check in at the beginning and say, hey, we have all of our ducks lined up in a row, and we feel this is a good way to move forward. But with life, things happen, and you might have to change that. So, it's not they're not set in stone. And I think a good thing that we should all live by is a little flexibility, and everything is good. But the QAPP itself at least gets people to start thinking about the things that they need to before they start jumping into actually trying to build the model. My personal experience is that we get really excited and we want to just jump into the data, and we want to look at it, we want to start playing with the numbers, and that's not, sometimes that could be a little counterproductive. It's good to step back at the beginning and try to get a holistic view of what you're trying to do so you can make the best decisions.
All right, I've got a bit of an easier one. Who approves the QAPP?
EPA, if it's an EPA project, we have staff that specifically look at QAPPs. And so we work together to get that QAPP to the right person for approval. And it's not a one-time thing. Sometimes we might send it back to an organization or entity that wrote it and say, hey, can you explain this a little bit more? Or I was hoping to hear a little bit more about how you were going to go out and handle this particular aspect of the model. So there can be iterations.
Another question, if a contractor can't begin work until a QAPP is approved, how can the level of detail in a QAPP be ensured if the money can't be spent yet?
Well, so that's kind of a difficult one for me because I don't do a lot of budgeting things. But usually the project should have budget to include a QAPP. And if it doesn't, then you should consider including budget to actually include a QAPP.
Thanks. Maybe I'll even chime in on an answer. You know, I've seen a few questions come through about, you know, are QAPPs appropriate to industry and states and other people? And I think it's important to note that, you know, everyone is going to have different requirements for a QAPP, and what Dino has talked about today is kind of the EPA-approved method for when we do work. But if you're a state or an industry person or a county or whoever, you may have your own requirements that requires more or less detail in your QAPP. So I think it's a good thing. And if you don't have any requirements, I think it's a good thing to be thinking about those. So just something to think about if you're not an EPA person listening in here today. And I'll get back to letting you answer questions, Zeno. How do you develop a good model if you're the project team? In other words, I'm in an agency, I'm the model guy.
So I'll just paraphrase that to make sure that I've got that right. How do you create a good model if you're the modeler themselves? Maybe you can repeat that.
I think the question is getting at, you know, what if you're the guy, and you know, maybe you don't even have a project team because people are busy or they aren't available in your agency. You know, how do you maybe I'll paraphrase. You know, if you're limited to just few people, how do you ensure that you're getting a good model at the end of the day?
Yeah, that's tough, and you know, I think modeling is a really good example of how it's really nice if you can have somebody just check your work, and to the extent that you could have somebody else in your office or in your organization review it for logic. They may not even have a lot of modeling experience, but if they can take a look at it and say, oh, wait, can you explain this because this doesn't make any sense to me. Just having another set of eyes wherever you can get them is really valuable. And the QAPP and developing that project team is really just an effort to try to get more eyes to look at the work.
Dino, another question. You mentioned the EPA guidance, and there's also other guidance documents out there. And I don't know if you have experience with these or not, but the one that came up is there's the CREM guidance, C-R-E-M guidance for developing QAPPs. I think the question is, have you looked at that? Do you have any experience using the CREM guidance versus the EPA guidance? And is there one you prefer more than others? Or maybe I'll even paraphrase, is there something altogether better than the EPA guidance?
Yeah, the CREM document that I think is being referred to is sort of more of a general overview of modeling itself, and it does touch upon, you know, kind of, you know, the topics that we're going to discuss in these 6 webinars. But the EPA webpage and the document that I highlighted for development of QAPPs specific for modeling really details particular items that should be included in a QAPP for modeling. You know, has there been any thought or consideration to the process by which you're going to step through calibration? Who is going to make the judgment call for that? So on and so forth. So those particular requirements for elements that should be included in a QAPP, and you know, the general procedures for how to create that QAPP, that's what's in that guidance. So it's really specific to writing a QAPP. The CREM guidance is more just general information about modeling as a whole. Both are great documents, though.
Thanks, Dino. I know many of you have submitted a few other questions, but I'm aware of the time, so I think we're going to get moving on now. And if we have some time at the end, we can revisit some of those. But now I'd like to turn over the presentation to Ben Cope. And Ben, the floor is yours.
Thank you, Jason. And I want to thank you, Jason, for helping lead this entire seminar series and keeping us all on the right track. So thank you very much, Jason. Okay, and thank you, Dino, for a great beginning to this webinar. Dino carried us up through having a good QAPP in hand, and I'm going to step through the step-by-step process by which we actually build one of these things. In our sort of agenda here, we're now into the second phase, and that's the initial development of the model, configuring the model to our system, to the problem at hand, and dealing with the data challenges. Okay, I'm going to go through a series of diagrams that show the building blocks of a model. And in this case, let's assume it's a one-dimensional longitudinal model. And say it's a river, for example. And it might be just a segment of a river. And the first thing we need to do is define the area within which we're going to make predictions. And that's oftentimes we say we're going to build a model of, and when we say that, we're saying the model domain is going to be what? And so we define that area within which we're going to make predictions. The 2 stars in this diagram are indications of hypothetical locations where we have data collected. And since this data is within the modeling domain, we call this calibration data. Okay? A little more about different kinds of data in a minute, but let's start with that. Model data within the model domain is we call calibration data. And then we also need to define our model domain so it matches the system we're dealing with. So for a river, we're going to have a channel shape defined. Oftentimes it might be very, many models just have a simplistic trapezoidal. You're going to have a trapezoidal shape, but you're defining those, the slopes of the banks, the width and the depth. Okay, so that's going to give you the, so now we have the physical dimensions of the model domain defined. Okay, then what we're going to do is we're going to chop the model domain into grid cells. In grid cells, we're going to have a calculation of water quality and all the other things we're going to predict. We're going to have one value within each grid cell. We can chop the domain into as many grid cells as we want, but there's a bit of a Goldilocks principle here. Too many cells is overkill, and if it's a very complex model, that's going to make your model run very slowly, and it's best to have a model that runs fast, because we're going to run this model a lot of times. On the other hand, if you have too few grid cells in your model domain, that's not good either, because as I said before, there's a prediction within each grid cell, And if we have very few grid cells, we're going to be predicting an average value over a very large area. Okay, so we want to have the right number of grid cells so that we can distinguish change within this system that we're modeling. Okay, now we go outside the model domain, and this is where we talk about the term boundary conditions. And boundary conditions are basically anything outside the model domain that influences the model domain. Okay, and these can be different kinds of influences. So the first one is a pretty obvious one I'm going to show you, and that is water flowing into the modeling domain. So if we just had a segment of a river chosen for modeling, for prediction, we'll have water flowing into that segment from upstream, and we call that the upstream boundary condition. I've put red dots on these, and then you'll also have water flowing in as tributaries. I put the red dots there, signifying data locations. Oftentimes, you'll want to start the model domain right downstream from where you have information. So you're feeding the model known, good information. I've made red dots instead of stars because we call these data different things. Boundary condition data is one thing, and calibration data is another. And we will distinguish these things when we're building the model because we want to make sure we have both, and we want to make sure the whole project team understands where we're feeding information into the model and where we're actually predicting water quality and then testing that against the data we have, that calibration data there. Another boundary condition is groundwater inflow. And groundwater can be a bit tricky. And we need to, with each of these boundary conditions, I should mention, we need to define, particularly if there's water coming in, we have to have the flow and the mass of all the constituents we're interested in coming in at each of these boundaries. So for groundwater, the flow, we don't measure groundwater flow. It's not like a USGS gauge. It's hard to know how much groundwater is coming into a particular location. So we oftentimes define the groundwater input as what's missing from the system between the river gauges. So we can back out what we estimate to be the groundwater coming into the system. But again, we have to define the quality of that groundwater as well. And that's a very difficult thing to do because we don't have a well-mixed chunk of water that we can sample. So, but we might have wells nearby that are sampled for constituents, or we might have seeps or springs coming into the river that we can sample to get a direct estimate of the quality of the groundwater. Okay, another boundary condition is not water flowing into the system, but rather the weather affecting the surface of the water. And we particularly need weather if we're going to be doing simulating temperature. And we also might need solar radiation to address algae growth. Finally, there's the bottom boundary, the bottom of the river. We have to define aspects of that so that we have the river flowing, physically, the water's moving in the way that we observe it moving. And so the roughness of the bottom must be defined. And there may also be fluxes of constituents in and out of the sediments that need to be estimated. And finally, there may be hypereic flow. That's water that's flowing underneath the river, basically. It's in the river sediment. It's not, the connection to the surface flow is transient, and we might need to estimate how much of the river is actually flowing as groundwater under the main channel. So each of these boundaries, we have to have data. And I think the word data is probably the most uttered word from modelers around the world because we are just obsessed with trying to get all the data we can. We don't want to miss something. And then we need a lot of it. Now, if it's a steady state model and you're just going to do a snapshot in time, perhaps this data, it's not that voluminous. It's relatively straightforward to get data, a single data point for each of these inputs. However, if you have a dynamic model, remember this is a continuously simulating model, you are going to have dynamic boundary conditions input into the model. So at each of these, with each of these inputs to the model, you need a time series input. And a quick note on that problem. Oftentimes we do have continuous information. A good example is the temperature sensors. They're pretty cheap and easy to deploy, and they give you continuous temperature. But there's other things like phosphorus, for example, that is typically a grab sample. And so for a dynamic model, say a boundary input for a dynamic model, you might have grab samples, the dots on this plot, and the model needs a dynamic input. It needs a whole time series that connects the dots. And we typically use linear interpolation to make that estimate. It's important to recognize, though, that the actual conditions between the two sample points are unknown. We've used the information as best we can. We just assume that there's a linear relationship in that gap. But it's one of the unknowns of the model, and it's one of many things that make models imperfect. Okay, so we've defined our model domain, and we find the boundary conditions that we need information for. And now the project, and you've done, well, let me back up. You've done your QAPP, and you, in the project team, you've talked about what you're going to model and why, and now it gets a little quiet because the modeler is going out to collect all this information and to configure the model. And this can take a fair amount of time where it goes quiet. Note the internet cable going into the cave. The modeler needs this because we are going to go out to the internet, and first of all, he has his computer in there, so he's building the model. But he's got an internet cable, not only for the internet, but he needs the phone as well. So where do you get all this data for the model? Much of it is obtainable from the web. USGS, a shout out to USGS. They are a treasure trove. We could not do the job we do without them. Treasure trove for flow, stream network information, water quality data, land cover data. Another important piece of information are state databases that are typically online and searchable, where we can get water quality data. You have the National Weather Service for weather data. EPA, if it has the STORET database, may be valuable for your project. So you can get a lot of stuff from the internet, but then you're most likely, I can almost say, you are surely going to need to pick up the phone and look into local data sources. And this is where the local knowledge on your project team can be really helpful, because you might need to be contacting point sources, irrigation districts, dam operators, etc. So you're going to have to pick up the phone and find that data. Also, there's many times previous studies have been done. We are building on the work of others, and you can contact potentially even the modeler who built the previous model, or just find out specific data for that was collected before. And finally, you might have actually collected data for this project. So it is possible that your project actually began with a parallel process of doing a QAPP for the model, as well as a QAPP for the data collection to drive that model. So in that case, in the best case, these things you have it all lined up where you know what you're going to build in terms of a model, and then you go out and get the data to support that model. That isn't always the case, but it's a good position to be in. So once the data is in hand, the modeler takes the typically data spreadsheets and has to create separate model input files that are in the correct format for the model software. Okay, and this assembly in a complex model can be a massive task, and as Dino mentioned before, we're all only human and mistakes can happen. So it's very nice to have team members that are willing to look into the files that you're assembling and to ask questions about how you fill gaps and how you anyway, just keep an eye on what you're doing because they may unearth mistakes. Okay, so that was a quick look at building the model files and getting the domain right and boundary conditions. Now we're going to get into the model calibration process. First, a quick step back as a reminder of what's going on inside the model domain. We've talked about boundary conditions in the model domain and grid cells, chopping the model domain into grid cells. Within each of those grid cells, you're going to be calculating the state of the system, and we call this state variables. And the variables listed here are just an example of pretty much all models will have to deal with the physical aspects, flow, depth, velocity, but you may have all these other parameters related to temperature, nutrients, and biomass. So this would be an example of a nutrient model, a set of state variables for a nutrient model. So the model is going to predict the value of each state variable in each grid cell. So in calibration, we're going to check that model estimate against measured values by lining up the grid cell location and the monitoring location. You might hear a skeptic say, and I've actually heard people say this very thing, I don't like models. That model is a black box, and we don't know what dark things lurk inside. And it is reasonable, actually, to be concerned about the makeup of a complex model. It's perfectly reasonable to be skeptical at first. But I want to assure folks that when we do it right, when we have a well-developed model and it's well documented, we know what's in the box. It's a model that's based on foundational, peer-reviewed science. The models typically have very detailed user manuals that list all the equations. The code of the model, the computer code, is typically open source, so you can go right inside and look at it. And then finally, as we'll go into exhaustive detail momentarily, the model is checked heavily against measured conditions. Talked about grid cells. Just one slide to point out that the grid cells communicate with each other. So each grid cell has its own mass and heat balance, and it's recalculated at each time step. But in addition to that, water and constituents and heat move from one grid cell to its neighbor. So the model is internally calculating the amount of water flowing across each boundary during each time step. And throughout that process, mass is conserved. Okay, so we've built the model, and we're now ready to give it a shot. We're going to run the model. Drum roll. This might be what you get. So this is just a generic plot of modeled versus measured conditions. So I'm going to show some more plots later that are like this. And this is typically what you would get from the Qual2KW model, which is a steady state model. And it gives you a snapshot of condition over space at one time. So this is, say, July 31st, 2007 in a river. And this is some constituent that you're measuring and simulating. And you hit run the first time, and it might be a little disappointing. And it's possible that only the modeler sees this result, because he or she is going to get to work to make this better. But the solid line is modeled, the squares are measured, and it's not, you know, we're in the ballpark, but it isn't that great either. So we might call this the initial error of the model. Now we're going to work on it. We're going to do calibration and troubleshooting and see if there's reasons we're this far off. We shouldn't be surprised that the prediction is off. environmental systems are very complex, and there's a wide range of things that might be causing the error. I've listed several of them here. And in the calibration process, one will be exploring each of these potential sources of model error. So the model calibration process is, I have a definition listed here, a test of a model with known input and output information. So remember, we've been talking about all the boundary conditions. These are known. We know what we're putting into the model, and we have the output, and we're running tests. In the second part of the definition, we're doing that to estimate factors that are unknown, for which we do not have data. The goal of this process is to improve the model accuracy. So we're diagnosing problems, much like a car mechanic. We're reassessing all the initial assumptions we made. We're doing trial and error with many model runs. We're doing sensitivity analysis, where we're fixing all the model inputs and changing one input alone to see if it has a big influence on the outcome. One part of calibration is to adjust rate constants. And rate constants are model inputs that increase or decrease the strength of a particular process in the model. So it's like a knob where you turn up or down the influence of a particular factor. So for example, algae biomass. If we're predicting that in the model, it can be influenced by both nutrient and temperature conditions. If we change the rate constants related to the strength of those factors, we can change the amount of algae that the model is growing. Excuse me. In a sense, we're tuning the model to bring it closer to the reality that we see in the measurements. Now, there are literature ranges for these rate constants. We can't just turn the knob as much as we want. We have to be within the range of literature rates that other folks have found to be reasonable for each of those rate constants. Another issue when we're looking at what's the source of the error, remember all those boundary conditions that we talked about before. Not all of them are directly measured. We have the groundwater we talked about that's difficult to measure. We might have, I threw a question mark up by the tributary. Maybe there's a tributary that's not measured at all and it's very small. And then I talked about the sediments. There may not be great information about sediment fluxes, and it's very difficult to know how much hyporheic exchange there is at the bottom. When we go through this calibration sequence, the calibration process is actually a method to the madness on one level, and that is that we do the work from the easiest things to simulate to the hardest. So for example, in a nutrient DO model, we'll start with the flow. Again, USGS typically has, we oftentimes have good flow information, and we can simulate that fairly easily. So that's the lowest hanging fruit. We'll start there. Then we'll go into other physical aspects, the water depth and the velocity. Once those parts of the model are working well, then we'll move on to water quality. And we'll often start with temperature, which is one of the easier parameters to simulate. And we'll also do temperature because the later parameters are dependent on our temperature simulation. So the typical sequence will be flow, followed by temperature, followed by nutrients and DO at last. Because dissolved oxygen, for example, is dependent on so many other parts of the model working right. Okay, so now I'm going to step through an example in a series of slides that give two plots, and one of the plots is a before shot, and the one is an after shot. These are again a Qual 2K model. It's a steady state snapshot. So you're seeing the river running from left to right, and the before is before calibration, and after is after calibration. Snapshot in time. July 31st, 2007. we went out and monitored this creek, and then we built a model to try to match what we saw on that day. The model is a continuous line, and the measurements are dots. And note that we make the model prediction continuous, but remember, we have a whole bunch of grid cells. It's actually, if you put the model in more granularity, put the model estimates, there'd be a whole bunch of dots, one for each grid cell that you'd be comparing. We just make a continuous line to make it easy to review how good the model's doing. But that continuous line is actually a series of dots, one for each grid cell. But the big dots are the measurements. Hopefully that I just made that clear. But so the first one is flow, before and after. In this case, we were overestimating some of the inputs in the upper part of the reach at first, and we were underestimating the flow at the bottom on the right-hand side. So we revised those estimates of inputs upstream. We made smaller inputs of flow upstream. And this would be things that are not measured. So we made estimates for inflows that weren't measured, and we were wrong. We were a little bit high. And then at the low end, we were a little bit low. So we increased the groundwater at the low end, for example, to bring that flow up. Okay. Again, we start with physical things, flow. Now we're moving to velocity. Velocity calibration for this particular problem is interesting because we have a wetland environment in the upstream reach on the left-hand side and a more flowing river, more typical riverine environment as you get about that midway point, halfway down the river. And in the top plot, the before plot, we were trying to match a particular velocity measurement by adjusting the physical aspects of the stream channel. It was throwing everything else. That particular part of the model wasn't working well, and we were trying to evaluate why. And we determined that this particular velocity measurement was higher than, was not representative of that part of the river. It had been taken near a bridge crossing, and the water had been funneled into a particular location which increased its velocity. So this is an example of a model actually identifying a piece of unrepresentative data. And as a team, you get together and look at this and agree, is it reasonable to drop this data point as something we're trying to match in the model? And in this case, we did. We dropped it, and we dropped the velocity down to what we saw elsewhere in that wetland environment. After the physical properties, we move on to temperature. One of the more straightforward water quality parameters. Note that here, qual2kW is a steady state model and gives a snapshot. However, what I didn't say was that it's actually quasi-steady state, and meaning that it gives a snapshot of one day. So we run 1 day variability into this model, and it gives you a min, a max, and a mean for that day. So that's why I have these hatched red lines. You have the solid black line is the mean estimate, and the hatched lines are the min and the max. So the temperature, minimum, and maximum. And for the data points, the black squares are the mean measured for that day, and the white squares are the min and the max. So we're trying to run that black line through the mean measurements. We're trying to run the hatched lines to match the spread in the data. And you'll see at the top plot before we're a little too, we have too much variability in the temperature on the left-hand side, for example. And when we calibrated it, we got a modest improvement. And this was made, if I recall, it was due to changes in the assumptions about hyperetic flow. Okay, once temperature is in hand, we get to the hardest part, dissolved oxygen, because it's dependent on everything we've done so far. Dissolved oxygen is dependent on flow, velocity, temperature. It's also dependent on algae, nutrients, organic matter, sediment, oxygen demand. There's a few things and I could go on and on. Those are some of the big things that affect dissolved oxygen. So this is a before calibration plot, and note that the measurements, I've circled an area of where there's a problem in the calibration. Note that there's a big daily swing in the dissolved oxygen that's measured, the spread between those two white squares, but the model has almost no fluctuation of oxygen at that point. And why is that? Well, it turns out that the algae predictions of the model at this stage in the model development were also very low, but that was consistent with what had been measured in terms of periphyton, the algae that grows on rocks. Turns out that we did not have information, or it wasn't in the model, in terms of macrophyte algae. Now, and this type of algae that's growing in big clumps on the bottom of a stream or on the sides is not captured by the protocol for the periphyte monitoring on rocks. So we had sort of a mismatch between our algae estimate and what's really happening in the stream. So similar to the velocity problem earlier, we had to sleuth and figure out if we were really matching the right algae biomass. We decided we were not, partly because we were not getting that signal of the dissolved oxygen indicated or plant matter activity or a high biomass. So we went back and we let the algae grow up to above what was measured on the periphyton samples. We did not have macrophyton samples, unfortunately, but we did have that visual inspection, and we knew there was a good biomass, a pretty large biomass of macrophytes. So we let the algae grow, if you will, and as expected, that makes the DO swing start to match the measurements. So this can get pretty messy in terms of the information you have, the information you do not have, and potentially even measurement error, as we talked about with the velocity example. Finally, just to point out that perhaps we've done all this work with the dissolved oxygen, we better go back and check all the other things that are linked to dissolved oxygen as we make these changes. So you might do a lot of stuff with dissolved oxygen like we just did. You got to go back and look at phosphorus, because they're so intrinsically linked. I got so excited there, I forgot how to pronounce intrinsically. Okay, so so as part of the DO calibration, we make sure that we're good on all fronts. We're checking all parameters. Okay, so that's my example of a steady state model. I'm going to just very briefly touch on what calibration looks like when you're not using a steady state model, a snapshot over space, but rather a dynamic model. Okay, so remember, a dynamic model is giving you a continuous simulation. So the x-axis goes from space to time. Now we're looking at one location. If you look at the top, it's River Mile 5, and we're looking at temperature over time. And we're again looking at measured versus simulated. This is a C=W2 simulation, continuous simulation of temperature. And you'll see the measured is the lighter color in the background, and the simulated is the dark black line. So a reminder that in order to have this type of model output and this type of comparison, you have to have the right data to both build the model. So you have to have continuous temperature, for example, information coming into the model domain, and you need to have this kind of calibration data where you can check how well the model is functioning. And finally, another example. Now we've moved to dynamic model. Now we're going to do a dynamic model, but in 2 dimensions. So instead of a well-mixed river, and we have one value for each location of the river, now we have vertical variation. So if this is a reservoir, which it is, and we are now looking at changes in water quality with depth over time. Okay, so this is another C=W2 simulation of a stratified reservoir, and we're looking at depth on the y-axis and dissolved oxygen on the x. And we have the simulated is the solid line, and the measured is the diamonds. And we want to try to match the vertical structure we see in dissolved oxygen. So it's a continuous model, though. So we have 2 different plots here because we can look at any time. And we're simulating through time. So we extract from the model its simulation for August 8th, because we have measurements that day, and we can see how the model's doing. And then we extract the output for August 29th, which was another sampling day. And so in this way, we can see if we're matching patterns over time in the vertical dimension. So there's many measures of model performance. And there are two general categories. When we're done with this calibration, we're going to have to write it up. We're going to write a report, and we're going to need to share or portray the quality of the model, how well it functions. And there's two general ways we do this. One is qualitative information, and that's what we've been doing in the last several slides. Plots and more plots. And you're just looking for pattern consistency between the model and the data. The second one is quantitative analysis, and that's where we actually look at those differences, and we look at the amount of difference between the modeled and the measured, and we calculate statistics about that difference. So again, with qualitative analysis, the number of plots, it can be an exhaustive effort. So back to Dino's example of a very complex model, this Neuse River effort, with each dot being a monitoring location where we're monitoring water quality, we're simulating it throughout this domain. You can imagine, and then with many, many parameters for a nutrient problem, for example, you can imagine how many plots you're going to be dealing with. And you're going to have an appendix in your modeling report that looks like this. And if the question, you might be asking, do you guys really look at all of those plots? And the answer is yes, we do. We might look at them pretty quickly, but we're basically doing pattern recognition, and the human eye is wonderful at doing this quickly. And so it's an integral part of how we evaluate models. So do the dots line up with the simulated solid line? That's the question. There may be other kinds of qualitative information that comes into play. This is an HSPF model, time series, and a couple of qualitative plots. Qualitative in the sense that you're looking at, so in the top left, we're doing a plot of the error with respect to the absolute value of the parameter we're simulating, which is flow. You look across this plot and you can see whether, well, do we have more errors at the top end or at the bottom end of our flow conditions? So that might be a qualitative plot that's useful. On the upper right, you might have a plot like this one that's shown just to see how is my, do I have bias either on the high end or the low end over time? This is a continuous simulation. Do I have any bias in the result? Now, we've gone through qualitative evaluation. Then there's the quantitative evaluation, the second type of way the second way we portray model quality. And you'll note that all the metrics, I've put 3 examples of model statistics, model error statistics on this plot. And you'll note that all of them on the right-hand side are measures of the model error as defined by the modeled value minus the measured value. So the mean error, the first one, note that that can be positive or negative. You can have a positive mean error or a negative mean error. If the minuses match the pluses, you know, if you think of all these errors and some are negative and some are positive, sometimes the model is above the measured, sometimes the measured is above the modeled. If those all match out, you have a very low mean error, and you can claim that the model has low bias. Okay, you're overshooting and undershooting equally. The absolute mean error, you'll note there, here we take the absolute value of that difference, and so they're all positive. Okay, so this is more of like an estimate of basically the mean error. Regardless of the sign, positive or negative, we're missing the mark by X amount. And then finally, the root mean square error, again, we're squaring that difference, so it's always going to be positive, kind of like the absolute mean error. But this is more of an estimate. We're getting a little fancier, and these statistics can get fancier still. I'm only showing 3 here. But this gives you more of a measure of the standard deviation of those differences. So your model report will have a bunch of plots, and then it'll also have a table of error stats. something like this one. So in this case, reading across the top of the table, you'll see we have the field sampling location. We'll have the model segment that's associated, that's at the same location as that field sampling location. And then we have the 3 error statistics that I mentioned previously on the last slide. You'll note the mean error, there's only one negative value there. I mentioned it can go positive or negative, so there is one location that we're under-predicting, but the other ones we're over-predicting. And when you do a grand average, this is a temperature model, you can argue we're biased a little bit high by about 0.5 degree Celsius in general, but not at that one location, but in general we are. And then you'll notice that the mean absolute error and the root mean square are always positive, and one can look at the grand average there and say, well, this model is between 0.8 and 0.9 degrees C of the measured conditions as a general matter. Okay, important to note that we're often asked, do we have criteria for what's acceptable in terms of these error statistics? And the answer is we do not, and I'll talk a little bit more later about why. But this is an example of a table from one research group that has offered its own judgment on what constitutes a very good, a good, or a fair model error for an HSPS model. Your project team can take this kind of information into account as you go through calibration, but you're not compelled to. You're not compelled to reach a certain error level. Okay. Well, and it may not be possible. Frankly, it may not be possible to reach some of those benchmarks that are being offered by others. More about that in a little bit. The reason we do both plots and stats, one reason is that if you just do error statistics, it's possible that you're missing an error that you could spot on a plot. So for example, you might have decent mean error with a low bias. You might have a root mean square error that's okay. But that doesn't tell you what the plot might tell you. So if you look at the plot of the model output, you see, well, wait a minute, I see what looks to be a time shift in my modeled versus simulated quality. So that may be something that you can fix in the model and make it more representative of reality, which is always our goal, and to match those measurements as best we can. So the eyeball test is very important and can identify problems that are missed in the error stats. Okay, so we've calibrated the model, we've written a report documenting its accuracy, and now we're getting toward the question of, is this model as good as we can get it? And we're moving toward model acceptance. Before you get to acceptance, it can be very helpful to have peer review. We've talked about peer review. Dino talked about it in the QAPP process. It can pop up any time in this model development process, but oftentimes it's this phase that we get peer review. I cannot emphasize enough how important it is to have a thorough model report. It makes every stage of the project run smoother. It helps your team. It's critical to having a good peer review. It's going to be very useful to stakeholders. And in the end, your lawyers may be interested in what you've written up there too. So peer review at this stage, just a general point is that it can really help you get to model acceptance. But it's very important to note that there's a graded approach to this. If you have a very simple, uncontroversial model, your peer review may involve informal, fairly informal peer review, and it could even be internal to your agency. You know, you're walking down the hall to a fellow technical person and asking for review. Typically, or commonly, these projects can be much more controversial and complex. It can even get to the point where you have a budget for peer review. You go out to external peer review, and you have panels, for example. You may, if you do that formal process, you will have charge questions. You'll be asking your peer reviewers specific questions, and you'll need to respond to those questions. It may be tempting to ask peer reviewers for their judgment on whether a model is good enough, quote unquote, to use. But remember that the model acceptance decision is ultimately a policy call for the agencies to make. What you want from your peer reviewers is pure science input. You are asking them to spot any technical problems that you've missed and to give you new ideas for ways to improve that model. This is a conceptual plot of how a project can commonly proceed with uncertainty high at the beginning of the project and reducing, and you could also say model error if you want to call the y-axis that label, and you're reducing uncertainty over time. The starred milestones might be internal or external reviews of the model. Eventually, the model accuracy is not improving that much with successive attempts to improve the calibration. So you have a situation where there's diminishing returns. So is the model good enough? As I mentioned, there's not fixed guidelines for the acceptable error. And why is that? I think it's reasonable that there aren't such fixed guidelines. First of all, Dino mentioned the wide variety of modeling challenges, the high variability of the high variation in the types of problems that we use models for. And the amount of, we can model everything from a small river segment to a three-dimensional estuary, small scale to large scale, simple parameters to extremely complex interlocked parameters. Situations where we have a lot of data, situations where we frankly don't have a lot of data, but we're still going to build the best model we can. Another point to make is that TMDLs, for example, is one regulatory product. In the statute itself, a margin of safety is mentioned, and that is a recognition that uncertainty is inherent in what we're doing here in terms of trying to predict environmental change. So at this point, the project team is sitting down and they're answering their final questions, such as, is the model capturing patterns in the data? Is the bias reasonably low? Have we addressed we had a peer review. Did we affirmatively deal with all the questions asked or suggestions made by the peer reviewers? And finally, is the team simply out of ideas for how to improve the model? And if the team has worked together throughout this grueling process, I've found that the consensus is pretty easy to achieve in terms of it's time to close the door and accept the model. This is a big moment because, as again, as I just said a moment ago, it was grueling. There was a lot of work done here, and the project team has had to be exposed to this model development process at each stage. And we're impatient to move ahead to do what we want to do, which is predict water quality for our regulatory purposes. So now we're ready to, we're done calibrating, we're done evaluating, we've got it peer reviewed, we've got a good model documentation report, and we're ready to run the model. And hopefully there is no going back. I wish I could say delete that word hopefully from the slide, but there are cases where we do have to go back. And examples might be that while you've done your best in reviewing this model, it's so complex that somebody still finds an error down the road somewhere. It could even be the modeler, him or herself, saying, you know, I looked at this thing again and I'm sorry to say I made an error. And if you do, you're going to have to recheck and make sure that that's a minor error, that it hasn't changed all the modeling results and blown up your calibration. Oftentimes, in my experience, you find small errors and they don't change things much, but you got to fix them in any case. Another potential is that, remember, the project team has accepted the model, but we haven't gone out to public comment, for example. And maybe there's many, many stakeholders poring over this information, and they find a new issue or a new concern in the model. You might decide to go back and recheck the calibration or make some tweaks to the model. But for now, let's assume that we're good and that's not going to happen, and we're going to move ahead and make predictions. And this is a slide I really liked that Jason presented last time that's depicting what we're really after here, which is predictive work. We want to know what happens if we improve a condition in the environment. What are we going to see in the receiving water in terms of an improvement? Now note that the solid line at the top there, where the highest phosphorus, and is called the existing condition. Remember, that's actually the calibrated model result. So in this plot, the person didn't put the measured condition on here, but that existing line is actually the model's estimate of the existing condition. And it's the same thing as your calibration run. The hatched lines below are the scenario results. So we've improved something and we're seeing phosphorus come down as we hope. The confidence in this prediction is built upon your confidence in the calibration and all the work you've done to build the model and document it and peer review it. Okay, with that, I am finished, and we have a fair chunk of time to answer questions. And I guess I'll turn it over. Jason, are you still there?
Still here, Ben. Thank you, guys. It was a really informative presentation today. I really appreciate it. We've got a bunch of questions that have come in. So once I get my screen to work again here.
Just ask me the easy ones.
So a few things from me. First of all, again, thank you guys very much. We've had I've been noted a number of questions today that I'm going to cover real broadly before we get into the details, Dino and Ben. One is there's been a lot of specific questions about QAPPs and are there example QAPPs, and I didn't know I needed a QAPP, and et cetera, et cetera. So if you are an EPA person or a state person doing an EPA-related project, there are people at EPA that do nothing but QA work. There's people in each of the regions and here at headquarters. There are also several websites related to nothing but QA and QAPPs, maybe not specific to modeling, but in general. So I'd encourage people, you can literally go into whatever search engine and type in EPA, QA, or QAPP, and figure out how, what kind of guidance is out there and do a search through our websites. Also, we can help you get in touch with any of the QA people at any of the EPA regions or headquarters if you need such a thing. And I would guess that for most of you, if you're a state or county or private industry, that there's probably somebody in your agency that does QA work that could probably help you address some of the broader QA issues that you might have with any modeling project or any project altogether, if it's monitoring or modeling or whatever. So I would encourage you to talk to them about that. Also, there have been a number of pretty technical questions about maybe Dean kind of in the weeds about very specific modeling concepts. So I'm going to kind of put those in a parking lot for now. And there are some opportunities to email one of the modelers specifically that have been giving the presentations either last time or today. And I think some of those kind of more in the weeds things might be better off for that. So I'm going to kind of focus on the broad overview questions that we've had today, and then onto the more the questions for you guys. Question number one: how can one calibrate a model for running scenarios if monitoring data related to these hypothetical scenarios are not available? How can extrapolation beyond the calibration data set be justified in such a case?
Yeah, there's two questions there about, in terms of the information to support the model scenarios. I'd have to know more about what the concern there is in terms of, because typically it is important when you do, and we're going to talk about scenarios I think more in the next webinar, but when you set up future scenarios, of course you're going to want to make those reasonable. And so if you're changing sources or changing conditions, you're going to want to make sure that, and we're back to the project team, when you make those changes, are those reasonable things that we're actually considering doing? I'm not sure that answered that question that well. Now you answered it, there's another aspect of that, and that is can you simulate beyond your data? Or in other words, you've calibrated the model to a certain condition, and now you're going to change conditions. Really, I mean, with a dynamic model, remember that we're calibrating to a lot of change over time. So you might, if you've got a complex dynamic model and you're simulating dry conditions, say you're simulating a whole year, and you've got dry conditions going pretty well, and there's a storm, and it's kind of matching that, and it's cold in the winter, and you're matching that, you start to build confidence that this model is representing, it's simulating the changes you see in the environment. So the type of model you have can sometimes build confidence that you can extrapolate using that model, because it's already handling the variation you're seeing in your data. Hopefully that, and Dino's here if he wants to add anything.
I think that was a good explanation. You know, I do a lot of work with HSPF, and you know, you're looking at the factors that go into the current existing model, land cover information and precipitation information, and if those don't change, well, that's fine. But even if they do, you know, the parameters in the model, they get tweaked in the calibration process, and so, you know, these scenarios of future conditions, you really are playing with the model, and it's the future. We don't know what the future is going to look like, but we're trying to use this tool with its uncertainty to give us some estimate of what that future is going to look like.
Thanks, guys. I'm going to, for folks out there, I'm kind of lumping and paraphrasing questions together, so if you don't hear your question exactly, my apologies. We do have quite a few of them. So I'm going to continue on kind of the data path here, and we've had several questions about the data that goes into your model, for example, monitoring data or air data or whatever. And what do you do about the quality of that data, and does that need to be included in your QAPP? And you know, how certain can you be that the data that you're using are good, accurate data?
Yeah, the answer is yes. The data quality you're going to use for the model is a topic of the QAPP. The QAPP should be talking about both the coverage, you know, the extent of your data, and as well as its quality.
I might add, you know, if you're looking at flow information and you're getting that from USGS, or you're getting precipitation or other meteorological information and you're getting that from NOAA, both USGS and NOAA have their own quality assurance procedures, and you should have confidence that those data as input for your model should be of a reasonably high quality.
And do you guys generally develop acceptance criteria for the data that, you know, might not be USGS or you know, they're from someone else, or how is that handled?
You know, I think that's probably something that we just handle on a case-by-case basis. You know, typically, as Dino mentioned, the information we're using is being collected by an organization that has good quality assurance programs. If there is isolated information that's coming from somewhere else, you're going to probably have to discuss that and maybe do some digging there. As Dino said, you're probably not going to dig too deeply into known good data sources, but you might dig into that question you just asked.
Yeah, and I think an organization that's generating the environmental data, you know, they're going to have to explain how they collected that information in their own QAPP. And you look at the quality of the QAPP. If they've thought about everything, or you know, it's, you know, a 2-page document that seems a little flimsy, well, you might take that into consideration and say, I don't know how I feel about this. And then let's say it's the only information out there and you have to use it. Well, you you keep that in the back of your mind, and when you think about the overall uncertainty in the model, you have to think it's possible. Well, it is almost always that any measurement in the environment has its own uncertainty and error involved with it. So it's not like these things are, we know for 100% fact with 100% certainty that I measured phosphorus as, 0.2 whatever units. Well, that's not true. It has its own uncertainty associated with it as well. So the whole goal is try to minimize all of that as much as possible, and the key is as much as possible.
Thanks, guys. I'm going to take a minute to do a little public service announcement. The audience will see on your screen the slide for our next webinar, which is scheduled for June 3rd at 1 p.m. Eastern, and it's going to build upon the first two webinars that you've heard now, and the next one's going to be kind of interpreting and using your model. So picking up from where Dino and Ben left off and actually putting some real-world application on how you go about using this to solve your water quality problem. But we do have quite a number of questions here left, so I hope people can stick around. So I'm just going to keep going here, and again, kind of paraphrasing. There's been a few questions about, how far do you take model calibration? Or maybe I'll say, how much time do you spend, and how do you know when to stop? It seems like you could spend a lot of time doing that, wondering, am I good enough or am I not good enough? Do you have any advice for people?
There's the common joke, you stop calibration when you run out of money. And I think Ben kind of highlighted the point is that eventually you're going to get to a point where you're putting in a lot of effort and you run out of ideas and it's just not getting that much better, and you just have to call it. I think the key is for calibration is you want to get the model to a point where it is reasonably matching with observed or measured information. It's never going to match everything perfectly, but what are you using the model for? If we're looking at a dynamic model and we want to look at, let's say, stormwater runoff, and the real thing we're interested in is those peak flows, those large storm events. Well, you might want to focus your calibration on those peak events and make sure that those match up well, because that's why you're using the model. You're using it to predict those sorts of events. And if that comes at the if other portions of the overall calibration suffer because of that, well, then that has to be. But it's tough to give a good number of when you need to call it quits. I think it's a tough judgment call, but there are folks out there that have sort of provided rules of guidance and general modeler rules of thumb. And I think we showed one slide that had that.
Thanks, Dino. Another question. When you're documenting your model, and I'm going to paraphrase several questions here. You've talked about several steps that go through model calibration and how you turn different dials to get it all honed in on the right answer. How much do you document that in your model documentation, your kind of those iterative steps? And maybe a broader question of just kind of what does your model documentation look like specifically at the end of the day?
Okay, I mean, it's, as I mentioned, the more the better. So we like big model documentation reports. And the question about how much of the iterative information is in there, typically we're documenting the final calibration. We're getting toward model acceptance, and we're saying this is the model as best as we can make it. Here's all the plots. Here's the error statistics. Here's the rate constant, a table of rate constants we ended up with, and that's kind of the core of the model development report. you might do some sensitivity information in addition to that focuses the reviewer to say that, here's some tests on what we thought was really important to the outcome, and this is where we put our effort on the calibration. So you might, I think it's a good practice also to tell people what are the big factors in the model that the calibration was focused on. But in general, you're documenting where you ended up.
Thanks, Ben. Another question. What tools are available to quantitatively evaluate how well a model is calibrated? Are there some publicly available tools, or is it mostly proprietary, or things you come up on your own, come up with on your own, or how does that work?
Yeah, so well, what I do is I actually just create plots myself of the data time series simulated from the model output and then the observed measurements, and I just plot them together. And I just use some spreadsheet software like Excel, and then I have developed my own calculations within Excel as well. There are other packages that I can't really think of off the top of my head that sort of look at calibration acceptance. But I think when in your search for whatever model you're using, you might find more information specific for that model.
Thanks, guys. And another quick public service announcement here. I've just advanced a slide to give the contact information for Ben and Dino, and include some acknowledgments for people that have helped out today. We do have about, I guess, 10 minutes left, so I think we will keep going with questions. Also, at the end of the presentation today, there's going to be a survey that's going to pop up once we're finished. We really do appreciate the feedback. We've already taken the feedback from the first webinar and used that to help to start to structure some of the later webinars. And we would definitely like to hear more from you guys today, either through the survey, or I do suggest that, or welcome you to send an email to myself, Jason Gilday, or Ben or Dino, or any of the others that have presented over the past 2 webinars. So. Okay, more questions. Is there a one-stop location to compare the different models that you've described today? And I think maybe this gets back at some of the stuff covered in the first webinar, but could you guys just do a quick overview for that?
Yeah, I think Tame mentioned in the first webinar some of the tools that EPA has produced on the web to talk about all the different, there's so many different model tools out there and what each one of them does. Dino talked about, the dimensionality. Some models are only one-dimensional, some offer 2- and 3-dimensional. Some are steady state, some are dynamic. So there are tools out there that Tame went over last time, and hopefully that's the focus of that question.
Yeah, I guess I would reiterate the first webinar did cover a lot of that stuff. It was recorded. It's archived. It's up on the EPA YouTube website. I encourage people to have a look at that for any kind of more of the basic general types of models, what is a model kind of questions that have been asked today. A couple of QAPP questions, since we have some time. Are there example QAPPs out there, or where could I find an example QAPP if I'm putting together a model for my agency?
Yeah, so that guidance for QAPPs specific for modeling, I believe it was G-5M on the EPA website that was in one of those slides. That actually has 3 different examples of QAPPs focused on a really simple model, an intermediate level of complexity model, and then a really complicated model. So that document itself actually has those examples within it.
And a question about model validation. I think the question is really what's the difference between, can you define model validation? What's the difference between calibration and validation?
Okay, you will sometimes hear a modeler say the model is calibrated and validated. And the idea behind those two terms is that you calibrate to one simulation period or condition in the simulated system, and then you blindly go to a different part of your observational record and you test the model against a different time period or a different type of condition to see that the model not only works for the data for which you calibrated it, but it works at say a different time. Completely sort of an independent test on the model. That's the idea. The word when you say calibrated and validated, it sounds kind of like I don't know. I have a little bit of concern about it because it sounds like, it's sealed up and it's shut and it's validated. We're done. And as I said before, you might not be done. There's always the potential you're going to go back and relook at your calibration. So I don't tend to use the word validation. I like to use the word evaluation or testing. And in fact, I oftentimes would argue that go ahead and take both those time periods, both your calibration time period and your quote-unquote validation time period, and just consider them 2 tests of your model and put them together and say, we're calibrated to both those periods.
Yeah, I might add, it kind of depends on the amount of data you have. Let's say you have a dynamic model and you have data from 2000 to 2010. And you've selected the years 2000 to 2005 to use as your calibration data set. And then once that's calibrated, you say, okay, well, let's test the model against 2006 to 2010 during the validation to make sure that the model predictions still hold. Well, that's fine, but let's say you only have data from 2000 to 2005. My personal opinion is that you would rather spend the entire amount of data simulation time to focus on calibration. But that is my opinion.
Thanks, and I think this is going to be the last question, but real quick, I've put up the next slide with a link to the certificate and a link to the archive for this webinar. I'll also I think take a minute to thank again Dino and Ben for presenting today, and I think, yeah, we have a few more minutes, so one more question, guys, and I'm kind of lumping a few questions here. If you have limited data, and I think this is pretty common, and you want to model your system, how do you know when you need to collect more? How do you know when you have too little or enough? And is there some rule of thumb or something that give people some guidance on when you actually do need to collect more data or when you have enough to actually begin your modeling project?
That's a very tough, broad question that I think sort of the word judgment call comes to mind. I mean, for example, one thing that'll halt you pretty fast is if you don't have any calibration data. So remember that I put that model, we have our model domain, and I said we've got some data within that domain that we can check our model against. If you are lacking critical data within the model domain, say for the parameter, a parameter that's really important to your project, that's kind of a deal breaker. So it is possible that you'll be going through your QAPP process and you'll say, I don't have any data for X, Y, or Z. And it may be a big enough problem that it stops you cold. On the other hand, there's never enough data. Let me go to the other extreme. I've been on projects where I thought, wow, we've got some pretty good data here. it seems like there's always somebody in the room who's going to say, I don't know, I don't think we have enough data. And sometimes it's the modeler, because we love data. So in the end, it's a judgment call, but yes, if you are really limited, very limited in data, probably everybody around the table is going to say, I just don't, I'm queasy, I don't like this, it's just not enough data. But I guess I would point out that I've also argued, there could be arguments about what's enough. We all have our own sort of benchmark or benchmarks for that.
Thanks, Ben, and thanks again, guys. I really appreciate your presentation today. I think it was great. I hope it was helpful to everyone out there. Just a quick note that the next webinar, again, is going to be on June 3rd. We'll be sending out a registration email to everyone that's registered for today, as well as getting the word out through some of the public channels that we've done before. So I hope you can all join in. This webinar will be, it has been recorded, it will be archived and posted to our website in a few weeks. It takes us that amount of time to kind of get everything processed, so just be a little patient with that if you can. And really appreciate everyone's participation. And with that, I think I will end the webinar. Thanks.